In this episode I want to talk about integer formats and linear light storage inside of these, and that integer format is hardly the right idea to work with linear light, and how Gamma comes to remedy that. And of course we try to avoid Gamma based formats for the linear light workflow in a huge way, and it gets even more complicated with other things. But for now we just explore this area. I have prepared here already something, and I want to introduce you how we can work inside of an integer with linear light and the consequences of it. As usual, in the cross point in the left lower area we have here our 0 value, and we decided that this is in this case our black value. And then, as the convention is, we have in our top value in the integer our 1.0 value, or just white. So I make here one stroke up, and the output here on the left side would be then also 100%. So I go here just and draw one of these lines here. Pretty straightforward. So what I have done here is to map out at the moment exactly always one stop and one stop and one stop. So when we have here from black the first stop in terms of light here, one stop, then the double amount of this would be one stop more, one stop from the camera. The next from the previous would be then here, and from that one it would be here, and then we are already on the end. And we can see clearly we have here only 5 stops. 1, 2, 3, 4 and 5 stops. This is not a lot of stuff inside, and we could have here smaller ones, but let's have a look how that maps here to our 100% and in straight values here. So when we say 5 stops is 100%, then half the light energy is 4 stops here in this case. So I draw now here a line, and this is only for demonstration purposes, and we would have a crossing point exactly here. For 3 stops, that would be half of the 50%, we would end up with 25, and that is pretty much here. So we go here and connect this, and then we have the half of that. Oops, I have to make that straight, and that would be 12.5. Okay, so I can already imagine where this ends, and then I can connect all these points. I try to make that straight, and the next one is then here. Okay, this is a little bit out of order, but you can see here it's a straight line. So where's the problem? It's linear light, it's all perfect, and we have 5 stops in it. Okay, again, 5 stops is not a lot, and we can see here that we used for one stop of the whole thing 50% of our data storage. And we have for the remaining 4 stops only 50% left. Let's make that a little bit more critical. When we take this area here, this is only 2 stops, but takes 75% of the whole data storage. And 25% is then only here 3 stops. Of course we could divide this here more and more and more, but you see here already it becomes so small that is nearly nothing. And when you think that we have mapped here now from here to here, and we take the worst case scenario 8-bit, then we have here 256 steps, then we have here maybe only 8 or 16 steps left. But here we have 120 or 127, whatever you like, in terms of steps for one stop. So this sounds not very, very useful at all. So when you keep in mind that we have maybe sometimes even 8 stops to discover the whole scene here from black to white, if we squeeze this in, maybe with some tricks, then these areas here are just not usable. because our target is, of course, to have for each stop at least a sufficient amount of steps to have a differentiation inside of that one stop. And to have only maybe 8 or 16 steps here, that's not really enough. So 127, and this would be then half of it, 64. Let's say that way, that we have here 128. So then this one here at 32, 16, 8, and 4 steps here. That would be nothing. 4 steps is, for one stop, pretty much the death of the picture. And so we couldn't make any color correction with it because there is no data available. So what to do with something like that? And for that I put everything away because I want to start over with something completely different. Let's say we want to have for each stop exactly the same amount. So I draw now here. Oops, I have to go here, and so we get the first stroke, then the next one, the next one, the next one, and the last one already. 5 equal lines here. And then I go from here up to our first, from here up to our second, from here up to our third, then to our fourth, and here we go then to the top one, 100% in both cases. So when I connect now all these crossing points together, then I get something that looks like a gamma curve. Surprise! And this gamma curve helps us now to create more space for the main area of our image that we want to store. And that happens, of course, over decades now in JPEG, in TIFF, and everything 8-bit that we have in this way. And the gamma curve has, of course, some other reasons to balance out a monitor, for example, but that has a deeper story than just a limitation. And there was, of course, more to it. And I will take one episode just for this. For now, I want to show you that we had before in the super bright area here 50%, and in the dark area here 12.5%, which equals 62.5% for 2 stops, as said before. And these are the 2 stops on the border, to the blacks, to the whites, where we have interest in because they define our image as well. But our eye is always attracted more to the middle tones of an image. We adapt easier to this, so we think everything super bright is not so important, everything super dark is not so important. Of course, that depends on the picture itself. I know. But normally we have in the middle field exactly what we want to have. At the moment we have here only 3.5% left. If we would have stored this along with the stops. But let's have a look. We have here 100% and 5 steps, so each step is 20%. So we have nice 20% here for the whites and the same amount for the blacks. And when we have enough input in this area, it will be mapped out nicely. And then we have 60% for our mid area for the 3 stops. And that will be even more if we have more stops here in the smaller area, of course, because then the dividing of this area here is even bigger, and the top and the smaller one will be the top and the lower one will be smaller. Okay, so from 37.5 to 60, we have made a huge step forward to 60. And I think this is now a more even distribution of our information. And a more even distribution of our information means also that we have a better differentiation among all these little steps. 256 when we talk about 8-bit per channel. And that pays off, of course, huge times when we want to manipulate the image in color correction, or when we have just to shift a little bit here and there. Okay, so you see, it wouldn't be a good idea to just use an integer as a linear light format, For that we have floating point, makes much more sense, especially for values beyond 1. And with the gamma curve inside, we have now here the option to store it nicely. And the gamma curve has survived not only based to be this kind of support for this format, it has survived also to counterbalance the screen, which comes very close to our perception of the eye as well. So we have there two things that comes together, and I want to talk about this in an episode on its own. And we will see that the gamma in storage and delivery formats might make a lot of sense, but it makes no sense in terms of pipeline, compositing work in 3D, where we can double maybe the gamma curve pretty simple and easy and get very dark results. Anyway, this was a short introduction to this theme or this problem and how it was solved in the past. See you in the next episode.